Hello, welcome to the Critical Design Review for the Optical Beacon Tracker for Optical Wireless Communications, the senior design project by Group 4 and sponsored by the Night Vision Lab. While optical wireless communications have existed for decades, maintaining clear communications requires precise alignment, which is difficult to maintain. The goal of this project is to build a device that can track an optical beacon while both the receiver and the beacon are mobile. Group 4, the team on this project, consists of Seth Johnson, who majors in photonic science and engineering, Blake Baez, who majors in computer engineering, and Raymond Lotus, who majors in electrical engineering. The sponsor for this project is the Night Vision Lab. The Night Vision Lab is a research group at Creel that specializes in infrared imagery and currently has research projects going on in subjects such as metasurface aberration correctors, vision-based navigation, and sensing technology from small UASs. For the overall diagram, it consists of a two-part system with the beacon and the receiver on either side. Both sides will have their own microcontroller unit, PCB, and optical design. All three aspects will be covered in depth by the end of this presentation.
Our project goals mainly center around detection distance. Our basic goals including the creation of a beacon strong enough to be detected up to 3 meters away, and a receiver able to track that same signal while indoors. Our more advanced goals include a little bit more distance. We hope to achieve at least a kilometer away between the two, and still be able to transmit and receive a signal. Our stretch goals involve transmitting and decoding a simple signal like an SOS from our laser diode.
In order to meet our project objectives, our team members will have to calculate the proper amount of optical power needed for our system. We must design and integrate the appropriate lenses on the transmitter and receiver side. We must also design a PCB for the beacon and receiver, and design a power supply that properly meets the system needs. Lastly, we must design algorithms that enable proper use to the gimbals, motors, QPD, GPS, and IMU inputs.
This table shows the specifications that we're going to meet by the end of this project. The rows highlighted in orange are specifications that we'll be able to show during our live demo at the end of the semester. These specifications include the beacon field of view, the stationary track accuracy, and the indoor functional distance. Other specifications, such as battery life, GPS accuracy, and outdoor functional distance, will be harder to show during a short demonstration.
Before getting to part selection and implementation, I'd like to take a moment and walk through the hardware block diagram. The 22.8 volt power supply on both the receiver and the beacon will need to be stepped down to usable voltages. For this we will be using both linear and switching regulators. From the regulators we have a slight variance in what we are planning to power from board to board, so I'll begin with the beacon side. There are three major components that need powering: the MCU, the LED array, and the servo motors. The switching regulator for the servo motors will have an output of 7.4 volts, while the other switching and linear regulators will be used to power our MCU and op amp with 3.3 and 5 volts respectively. Lastly, our LED array will be powered directly from our 22.8 volt battery, but controlled via a solid state relay. The LED array will then emit light into collimation lenses and sent to the QPD. In the situation where no signal is received, the telemetry module will relay positional and orientation data to and from the receiver to roughly align the array with the QPD using the gimbal and servo motors. Moving on to the receiver side, there are only two regulators: the switching to step down the 22.8 volts to 5 for our op amps used in decoding and amplifying the QPD signals, and a linear regulator to further step down the 5 volts to 3.3 in order to power our MCU.
In this section, we're going to cover the optical design and hardware selection, which was done by the photonic science and engineer Seth. This slide shows the optical design for both the beacon and receiver systems. On the right, we have the beacon system, which consists of a 1550 nanometer laser diode, which is coupled into a single mode fiber, exits through a output expander, passes through a dichroic mirror, and then exits out the diverging lens. On the bottom right, we have the 850 nanometer LED array, which passes through a diffuser plate, a collimating lens, and then reflects off of the dichroic mirror and then passes through the diverging lens. On the left side, we have the collecting lens, which focuses the light into the quadrant photodiode. The spot size for the array will be larger than the spot size of the 1550 light source. And then the 1550 light source will pass through an optical fiber, which is coupled to the inside of the quadrant photodiode, and go onto a 1550 nanometer photodiode. Once the light has focused into the 1550 nanometer laser diode, we'll know that we have a perfect alignment. When choosing the 1550 nanometer sensitive photodiode, we chose the Thorlabs FGA015. While the other photodiodes on this list may be more efficient, the specifications for the FGA015 are sufficient, and it is the cheapest option. When choosing our quadrant photodiode, we chose the SPOT-90-0. You may notice that there's no table comparing this to other photodiodes, and that's because this one is unique with its 200 micron laser cut hole in the center. This will allow us to couple a fiber optic cable into the center. So that way, when we're aligning our LED array and our laser diode, we can check perfect alignment when the laser diode goes through the center. To choose our LEDs and our laser diode, we use the equations on the left to calculate the necessary output power in order to meet the minimum detectable power of our photodiodes. P-ints is the incident power at a given distance, P-out is the output power of our beacon, AD is the area of our receiver lens, AB is the area of the beacon the beacon beam at a given distance. Using these equations, we can calculate that the output power of the beacon can be no less than 450 milliwatts for our 1550 nanometer laser diode, and no less than 164 milliwatts for our 850 nanometer LED array. Using the equations in the previous slide, we've chosen the Advanced Photonics CBLL95-90 because it has the most output power per dollar and it has a reasonable threshold current. For our LEDs, we chose the AMS Osram SFH4258S. It has an output irradiance of 100 milliwatts per steradian and a viewing angle of 30 degrees. In a 5x5 array, the total power would be 2500 milliwatts per steradian, which roughly equates to 535 milliwatts within the 30-degree viewing angle. Using our lenses, we calculated them in Zmax, by hand, and via physical testing. We chose 4 lenses, which all have the Edmund Optics near to AR coating, which provides a 98 to 99% transmission at our required wavelengths. For our collecting lens, it is 1-inch diameter, f equals 16 millimeters on the receiver side. On the beacon side, we have the diverging lens at 25 millimeter diameter and negative 100 millimeter focal length. The fiber output expander is 6 millimeters with a focal length of negative 6 millimeters. And the array collimator is 30 millimeters, so that way it's sufficiently large enough to cover the LED array. The last items for the optical design are the dichroic mirror and the transmissive diffuser. The dichroic mirror's property allow it to transmit certain wavelengths while reflecting others. So we chose the 87-040 from Edmund Optics because it has 99% reflection at 850 nanometers and 90% transmission at 1550. For the diffuser plate, we chose the ED1C20 transmissive diffuser, which has a 90% transmission and relatively minimal divergence incident. This picture shows the testing that we did on our optical design. All of our lenses and our LED and our laser diode are currently in our possession. However, the LEDs are surface mount, so they cannot be tested until we have our PCBs in hand. It's hard to see, but on the right, the light is going through our collecting lens and incident onto an infrared card. It's hard to see the array because the laser is so much brighter, but the spot size was as expected.
In this section, we'll be looking at different hardware that we compared and contrasted and ultimately made a decision on, and the PCB design, and how we plan to implement the hardware in which we selected. While combing the internet for possible MCU solutions, we found a few that seemed to fit our needs fairly well. Ultimately, we decided on the ESP32 S3 Mini N8 due to its better processor, larger flash memory, and availability. Additionally, it has a built-in antenna which could allow for further signal transmission between the Cube Orange and our ESP32. While selecting voltage regulators, it became apparent that it would be easier to use the same regulators for both boards. That is why we landed on the LMQ 61460. Even though it has a max output current of 6 amps, we only plan on setting that to 3 for our laser diode. For our other components, however, we won't be coming anywhere near that. But again, easier to have the same component for all. When it came to the linear regulator, since we were only going from 5 to 3.3 volts and powering our MCU, it seemed suitable to be using the TLV 75801 with a max output current of half an amp. Overall, our selection was based on availability, price, and ease in the sense of using the same regulators. When comparing and contrasting the different servo motors, we found 3 that would be suitable for our project. And although the Power HD and Tower Pro had higher torque and lower weight, we decided to go with the Savix based on its higher speed, weatherproofing, and metal gears.
The gimbal we chose is the Grimsey T3 V3. This gimbal was donated by KVL. However, it was within budget to purchase something else if needed. The reason it was chosen was because of its high stability and smooth motion control, ease of integration with GPS modules. It had an adaptable mounting system, and it was lightweight compared to its strength. It also, on that note, met our 5 kilogram requirement for the total system on either the transmitter or receiver side.
Moving on from hardware selection to PCB design, this is an overall schematic of our receiver, and we're going to get into detail section by section. In this section, we'll be addressing the power supply selection and regulation. We'll have 2 potential power supplies, one being a USB-C, which will be used for programming the board, and the other one will be our battery supply as previously mentioned. Both of these will have an output of 5 volts. The battery, after using the switching regulator, and the 5 volt USB-C receptacle. Both of those will go straight into the toggle switch that you see in the center of the screen. That toggle switch will allow us to switch between battery power and USB-C power, both of which will be run through the same 3.3 volt linear regulator. A brief overview of our MCU connections. You'll see that we'll have a reset and a boot button connected to our enable and GPIO pins. In addition, we will also be having a 6-pin out UART connection and a 4-pin out SPI connection. Additionally, we'll also have to receive 3 different signals from our QPD, a numerator X, numerator Y, and denominator, in order to calculate the positional data digitally. The amplifiers for our quad cell photodiode can be divided into 2 stages, transimpedance amplification and summing and difference amplifiers, to create the necessary values to equate position. Unlike the quad cell photodiode, our single cell photodiode will not be used for calculating position. Instead, its 2 stages of amplification involve transimpedance and then just further gain and filtration. We are simply looking for an on or off signal from our single cell photodiode. This is what our PCB will look like after laying out and tracing all of the components on the board. Moving on to the beacon schematic, at first glance you'll see our LED array, our 4 voltage regulators, and then some similar things like our power supply connections to USB-C and our battery. As previously mentioned, we'll be using 2 separate switching regulators and 2 separate linear regulators, unlike before. But the only difference is this time we'll be switching a 3.3 volt output from our linear regulators on our toggle switch to power our ESP32 only. This will allow us to power up the rest of the board without potentially harming the MCU. Going over the MCU connections, again there's plenty that is similar to before, but this time there's a slight difference with our temperature sensor and RGB for temperature indication light. Additionally, we'll be having our 6 pins for 2 different servo motors at 2.54 millimeters. Because we are powering our LED array straight from the battery, we'll be having 4 series runs, all in parallel. The first 3 series will be of 6 LEDs, while the last one will have a 7th. Each resistor value will be calculated based on the size of the series and the input voltage. Furthermore, for modulation, we'll be using a solid-state relay, which will be controlled by the MCU, but the signal from the MCU will have to be ran through an op-amp, same as the ones we were using on our receiver. And finally, we have our PCB layout for our receiver.
Software selection and design. This is our initial brief software diagram for how the whole system logic will interact. The transmitter side is on the right and the receiver side is on the left. Along with the programming language, the embedded system we chose to use was important, just as important. The support for the language needed to be present in order to use said microcontroller. So the option we chose was C. The reasons I will explain below. C is the only imperative procedural language of the following that we chose. It is also has the greatest support out of all the embedded systems, the next being Java. The performance is the highest along with C++ compared to Java and Python, that being that they are object-oriented programming languages. Java has support for a JVM that allows it to have a better performance, but it still does not match C in terms of support nor performance. The memory control is low level for C and C++ as well. This is not the case for Java or Python. The next choice, if we did not choose C, would be Python, solely to use the Raspberry Pi. However, we ended up going with an ESP32, so C was our obvious choice. Communications protocol. The two main communication protocols we plan to use is I2C and UART. This project will mainly be using UART. The reason is because the GRIMSY and GPS modules require the communication using UART. We left I2C as a possible choice for the telemetry module. However, there are some drawbacks to I2C that I will list. Now, in our case, it is more complex and requires addressing as compared to UART, which does not. It is fairly simple. One may say it's nearly plug and play with very minimal setup. Now, they will both have possible or same use cases for each of the modules that we're using, such as the telemetry. But if just in case we have issues with either the UART or I2C communication protocols, we might switch which one we're using for that particular subsystem. Key concepts in algorithms and system control. This system will have a search algorithm for finding any signal. This system will have an alignment algorithm for establishing the signal with more precision. It will have control theory, and it will have signal processing. For the alignment algorithm, which is the more precise algorithms, we initially chose between two, conical alignment and radial alignment. Our final decision went to conical. Conical alignment involves adjusting the alignment of two systems or components by rotating one of them around an axis in a conical pattern until optimal alignment is achieved. It is generally more complex than radial. However, it covers all angles, which we require. As for the initial search algorithm, we had two available options, the golden section search and the spiral search. We ultimately chose the spiral search. Searches for the optimum by moving in an outward or inward spiral from a central point. In this case, it will be an outward to inward. It is less efficient if you were pertaining to a 2D space. It is not guaranteed to converge, but that will not be needed. And it can be computationally expensive. However, this doesn't hamper on performance, so that was not considered. Control theory. For this, we are attempting to implement the Kalman filter, a mathematical algorithm used to estimate the state of a dynamic system from things such as noisy measurements. It is useful in a sensor fusion where data from multiple sources need to be combined. It is useful in a system that requires real-time tracking. This is a real-time system that employs tracking. Can be used to predict the state of the transmitter and receiver. However, it can be complex for nonlinear models, which this is, and it requires tuning. So it will require a lot of tuning to dial in to make sure that the precision in the system is kept. For signal processing, we will be employing interpolation, which refers to estimating intermediate values between discrete data points in a signal, often to increase the signal's sampling rate or improve its resolution. This can improve signal quality, can correct timing errors, can also help upsampling or downsampling, and it ensures efficient data recovery. Those last 2 points are more towards communication, which will not be employed in this project. This project pertains to a larger project that someone else will be employing, and that involves utilizing our optical beacon tracker for communication. This is a diagram of our receiver sequence. It is a logical sequence on how the ESP32 on the receiver side will operate. Here we can see the same type of diagram for the transmitter side. In the two following images, you will see the testing of our motors and gimbals utilizing the ESP32 microcontroller. This is similar to what our UI is going to look like. The system will do most of the work by itself, and the user's only job is to start or stop said system.
Budget for this project was provided by the KBL Group, who donated the expensive equipment, such as the Grimsey T3V3, as well as a budget of $5,000 for the other items we might need. Certain disposable equipment, like the through-hole LEDs that were shown during the optical setup, are paid for by the team members because they are disposable.
Here we can see a graph of our total expenses for this project.
The work distribution for this project is as follows. Seth Johnson, our photonic science engineer, performed the optical design, the optoelectronic hardware selection, and will physically assemble the beacon and receiver due to the sheer amount of optics involved. Raymond will assist. Blake Baez is in charge of software design, MCU and GPS selection, and designing and maintaining the website. Raymond Lotus, the electrical engineer, will be doing the electrical and PCB design, as well as the electrical hardware selection. He will assist Seth in physically assembling the beacon and receiver. Moving forward, we currently possess almost all of our hardware, however, we're still waiting on our PCBs to arrive. By October 16th, we should have tested our first PCB and the beacon will be operational. By October 16th, we will also be able to control our gimbal using inputs from our GPS and our photodiode. This has been the Critical Design Review for Group 4, Optical Beacon Tracker for Optical Wireless Communications. Thank you.